Good afternoon, everybody. Rod Barrett here. Welcome to the next Lunchbox seminar. So our speaker today is Dr. David Painter. David is a research fellow in the Hopkins Centre, part of the Menzies Health Institute. He's based at the Nathan campus. He works as part of the Beehive group. The Beehive group works out of the Brain and Enriched Environments Lab. I think I got that right, David, at the Nathan campus on level 0 there. David's got a background in psychology, and you might have just heard him explain where he did his PhD, which was at the Queensland Brain Institute. And he's going to be talking to us today about some of the work he's been doing over the past few years in using virtual reality to assess and rehabilitate people that have had brain injury. So, David, thanks for joining us today. We're really looking forward to this talk. I'm sure there's a lot of people across the school who will be very interested to hear what you have to say. So I'll hand it over to you. Thanks, David.
Well, thanks very much. And thanks very much for the invitation to speak with you today. Yeah, my name is David Painter, and I'm a research fellow working with the Hopkins Centre. Today I'm going to be telling you about mapping spatial attention following brain injury using virtual reality. As I find the forward button, I'd like to acknowledge my collaborators at the Hopkins Centre, Gold Coast Health, Metro South Health, and the Florey Institute, including but not limited to Professor Heidi Zeman, Professor Elizabeth Kendall, Michael Norwood, Dr. Camilla Shirota, Connor Reed, Dr. Trevor Hine, Sally Stewart, Dr. Daniel Harvey, Professor Julie Bernhardt, Susan Jones, Dr. Ben Chen, Callie Dungy, Christy Woodman, Dr. Leslie Gann, Christy Yu, Dr. Marilia Liberia, and Catherine Delaney. Apologies for the mispronunciation. Obviously, this project is much bigger than just me and involves collaborations with people in the clinical space. I'd also like to acknowledge the funding sources, NHMRC, Metro South Health, and Bionics Queensland. The project really centers around a particular neurological condition, unilateral spatial neglect, which is a problem with attention that most commonly follows right hemisphere stroke. Here is an individual with neglect, and as you can see, they're looking off towards the right side of space, and it's as though objects falling on the left side of space don't exist. It's not a vision problem. If you have a completely empty world and you just have one object on the left, the person is able to find it. The problem becomes when there are multiple objects simultaneously present. Under those conditions, objects on the right sort of win the competition for perception and awareness, and those on the left lose and become neglected. Now, here is a video of people with neglect describing what it's like. And this is actually quite rare because one of the symptoms is a lack of awareness, that you're unable to have insight into what you can and can't perceive, which is one of the paradoxes of neglect. And I apologize, the audio isn't available at this time, but I'll send through the link to the YouTube where you can hear the audio. And I'll just describe what these people say. So here they're talking about that classic symptom where you have the inability to finish your meal, that you're just eating food on the right side of the place. And one of the gentlemen says that it's a problem for him because he used to be a cook before he had a stroke. And so now he can't cook, he can't even eat. And this was probably the most insightful of a person with neglect. And they're describing sort of the extent of that and you can't see. And they're saying that objects on the, it's as though there's nothing on the left. Everything is sort of condensed over to the right side of space. So it's hard to know what another person perceives, and it's hard to know what neglect may be like. Here is a cartoon version of what it may be, and this is sort of what we're trying to understand in these research projects. So this is normal attention. Here is a complex scene with flowers and buildings and so on, and you're able to direct your attention to each of those locations in turn to perceive the various objects. For the person with neglect, it's as though the left side doesn't exist and only objects on the right. And so that's quite remarkable that you could have a salient object like a building that just doesn't exist in perception for that person. Neglect affects approximately 50% of all acute stroke survivors and is usually accompanied by functional disability. It's a stronger predictor of post-stroke recovery than paralysis or communication disability, and it's often associated with poor rehabilitation outcomes, for example, an inability to return to employment. In Queensland, there are approximately 77,000 stroke survivors. 39,000 of those may have neglect, although the estimates vary between 30 and 70%. And there are 15 stroke units in public hospitals that could potentially benefit from the technology that we're currently developing. So why does this happen? It comes down to the nature of being an organism in the world. The world is a complex place, and this is kind of an exaggeration, but it gives you a good indication of the problem of attention, that there are just so many objects, and to perceive them, you need to look at each in turn. A quick glance at the scene reveals water, it reveals a beach, there are people on the beach, there are boats, and that's sort of your immediate first pass. And then any further details, like a person sitting on a rug or so on, those are things that you need to deliberately attend to find. And obviously this is your classic, where's Wally or Waldo, depending on which country you grew up in, and you need to find him, and it's challenging, but he happens to be in the center there. Part of this trick is not only that there are so many objects in the scene, but the object of interest, a person with red and white stripes, shares features with other objects, which is creating a confusion. So everything kind of looks a little bit like Wally. Quite a bit is now known about the functional neuroanatomy of attention and also the neuroanatomy of neglect. It's beyond the scope to describe those results in full, but there are two broad classes of study. One is a functional magnetic resonance imaging study where the person's in the scanner and you're looking for patterns of blood oxygenation as people perform particular tasks. Another type of study is a structural imaging study, and this is a structural imaging study here, where you can correlate particular behavioral patterns, in this case neglect severity scores, with particular regions of the brain, for example, gray matter density. And there's converging evidence from various sources of information, neuroimaging, lesion mapping studies, that suggests that attention is lateralized to the right hemisphere of the brain, that there are particular regions, particularly in the parietal lobe and other regions in the frontal lobe, that are important for directing your attention in space. Particularly the parietal lobe, you have a middle cerebral artery that feeds up into here, innervating this area with blood supply. That's a key place for stroke and blockage, and so the cell death that you have following a stroke is kind of at a important region for attention in the parietal lobe, but there are other regions, frontal cortex and subcortically beneath the surface that could also be associated. But the take home is it's a right hemisphere lateralized network, and damage to it can produce problems with your attention. Now, in the clinical setting, neglect is often assessed using pen and paper methods. And here are sort of three examples. One is a cancellation task, kind of like the Wally example, where you need to find a particular element here in A and just mark it off in a complex array of distractors. And the person marks on the right side of the page, indicating that they have neglect. They can't find A's to this location, for example, or a copying task where you need to draw a clock. And here you can see all the numbers of the clock are compressed on the right side of space, indicating neglect, or a line bisection. You need to draw the midpoint of lines, and sometimes it's off to the right. If you're drawing off to the right, if you think that's the middle, that's a good indication that you have neglect. So our research question is sort of how do these traditional and widely used pen and paper tests compare with emerging virtual reality methods? And is there anything that we can do with this sort of high-tech approach that we couldn't do using these classic methods? So as mentioned before, I'm part of the Beehive stream, where we're interested in positive environments and designing environments in a way that can have good implications for people with disability and in their recovery from injury and their rehabilitation into society. And virtual reality is a technology that conceptually fits with that, because you're able to provide a perception of an artificial virtual environment that could have the characteristics that you think could be useful for helping recovery. The key element, obviously, is a person's wearing a headset. Inside the headset, there are two displays, each projecting a slightly different image to the two eyes, thereby creating a perception of 3D space. Because you're wearing the headset, you're in that 3D space, and it's as though the external world temporarily ceases to exist, and your new world is the world of your perception that's generated by the computer. VR has a lot of useful characteristics that make it suitable for investigating human behavior and perception. One is the facility for motion capture. We can measure the way that the headset is moving. The person also has controllers in their hands that they can use to interact with the world. We can measure those as well. We can measure where the person is looking in space using their headset as a sort of reference point. Modern headsets also have eye trackers in them, so we can measure where the person is looking in space. And an important aspect is that VR came mostly out of the gaming tradition, and that means that it's ideally suited to sort of maximize the fun factor, and that has the potential to create rehabilitation scenarios that are maximally engaging, motivating, rewarding, that want the person to come back and try them again. And so it has the potential for good compliance. At the moment, there are a series of games that are well developed and sort of mainstays now of VR, Beat Saber, and Tetris Effect. For our context, the important thing is that we have precise control over the environment, and that allows us to investigate perception in neglect. There's a lot of VR systems on the market, and it could be slightly confusing, and indeed it is confusing. Since 2016, there's been the first wave of consumer-grade headsets for the mass market, and there's quite a number of nice devices now available for use, and they range on the dimensions of portability and fidelity. You have highly portable systems that don't require external computers that you can walk around with without cables. Then you have high fidelity systems with external tracking devices, cables, and powerful computers that give you a rich experience. And those are the systems that we're focusing on here in the inpatient rehabilitation context to provide the best possible experience for people in the clinic. And here is an example of the most popular VR game at the moment, Beat Saber. You need to slice blocks that come to you in time with the music. And you can see that you can get quite good at this with practice. Of course, individual differences, some better dancers than others. I have not reached this level of proficiency, but you can get better at the task. As a quick aside, we know that video games can improve attention. This is shown through converging evidence of cross-sectional and interventional studies. Cross-sectional studies are those that take action video game players and non-action video game players, compare their attentional performance, and find a benefit for people to play action video games. So there's kind of a nature-nurture question there. Is there something inherent that draws people with better attention to action games? And I am speaking on average, of course. These are group average results. So to answer the nature-nurture question, you can do an interventionist study where you take non-gamers, allocate them to action games or control games, and again, you find a significant benefit on average for those allocated to action games. Now, VR, the idea of using VR as a means of measuring attention in neglect is not new. It dates back at least to 2012. In this study, the authors used a prototypical VR system before the first wave of consumer devices on the market. The person is viewing an array of elements that are appearing to the left and right and also in depth. The person's task is just to cross off all these different elements, and you can map behavioral performance as a function of position. In this case, you are looking at reaction time, and the larger the sphere, the slower the reaction time. So people are obviously slower to objects appearing on the left. Additionally, they're also less accurate. So the smaller the sphere here, the less the accuracy on the left-hand side of space. An early indication that VR can map attention and neglect. Here's a more recent study using modern technology. They had a similar concept of objects appearing around the person, in this case, cubes and spheres. And I believe the person's task was to ignore the cubes and just indicate the spheres. So avoid the cubes and track and point out where the spheres are. What you can do is you can calculate how many targets were found on the left versus right. That's your center of cancellation metric, and positive values here reflect a rightward bias and inattention to the left of space. Here's pen and paper tasks. There's a bias for neglect versus healthy, obviously. And with VR, you find a similar thing, that there's a bias for neglect versus healthy. The authors argued that results were statistically comparable between pen and paper and virtual reality in their experiment. So we've been developing technology along those lines, which we've termed the Attention Atlas. A person in VR finding objects that are presented around them systematically in space. One difference to our approach to the previous ones is to systematically work through a range of different stimulus characteristics to find the optimal stimulus for best discriminating neglect versus non-neglect. Here is a 360 view of space, so we can also do it not only in front of people, but around them, and present objects systematically at even distances and see performance at each of those locations. We can vary the overall structure of the array by varying the depth. We can vary the surface upon which the objects are presented. In the following examples, everything is presented on a spherical surface. We can vary the density of objects. We can vary how far away they appear in space. We can vary the target and distractor properties. In this example, search for a T among rotated T's. In this example, search for a 6 among rotated sixes, which happen to also be nines. Because this is intended for people with brain injury, we try to keep it as simple as possible. And here's an example of how we try to simplify to explain what the task requirements are. So to do this task, you need to sit down, you need to put on the VR headset, you're going to see some letters, you need to find a particular letter of interest, in this case a T, you need to point to that, you need to press a button, and then the next trial will begin. It's not by accident that these previous examples have been using T's and L's. T's and L's are just one example of a category, but they're a good exemplar of a stimulus that maximally captures the essence of selective attention. So here your task is to find a T among L's. In this case, all the L's are arranged neatly, performing a grid-like pattern, and the T is quite apparent. Here is an L, it's in a different color, it's readily apparent in this display and quick to find. Now, what happens when you rotate the T's, rotate the letters, including the T and the L's, you see that the T becomes less easy to find. And this is taken as evidence that the defining characteristic of T versus L, the location of the intersection, is not an element, is not an attribute that can guide your attention. You need to search for each of these elements in turn until you happen upon the T. Whereas with the color, you can see that the color is invariant to the rotation. Therefore, the color is a guiding attribute that you can find irrespective of the number of elements in the array. Here is a demo version of the attention atlas. Looking here on the left side from the third person perspective, from the outside looking in, so to speak. And on the right side, this is what it looks like from the first person perspective in VR. The person's task is just to find a particular target, a 6, among rotated 6s. And this is just showing that we can easily vary the stimulus parameters on a trial-by-trial basis to assess different aspects of attention and to assess the effects of the stimulus properties. Here we're looking at a sort of lower density, for example, that's appearing further away from the person, or we can have a higher density closer by, and so on and so forth. We can vary these parameters to see how the person pays attention under those conditions. This is a example results output that uses this raycast procedure that I had previously described as sort of innovative in our approach compared with previous examples. So the idea of the raycast is simply that you draw a straight line between an object of interest, like the headset, and the spherical search surface. That intersection point is your point of attention. We can do that with the headset. We can do that with the controller. And not shown on this diagram, actually, we can do that with the eye tracker. Obviously, the head can be fixed in position and the eyes will move about. So under those conditions, we're able to see also where the eyes fall on that search surface. Here is an example of a search in 360 degrees, so completely surrounding the person, with red being the headset attention, blue being the eye attention, and green being where the controller is pointing throughout this. Like the previous studies, we can also measure accuracy and reaction time for each of those targets. But the key aspect is really these maps that we generate, that we can look separately for each of these different sources. This is where the headset is positioned, and you can see that the headset here is fairly centrally positioned, and that the eye is also centrally positioned to the left and the right. The headset does a little bit of the work. You move your head a little bit to find the target, and then the eyes do the rest of the work in line with sort of conservation of energy eye movement is relatively less biologically expensive than a head movement, and so that does the majority of the work that the head movement doesn't do. This is where the person is pointing in space. In this example, there are 19 elements positioned around. All of this data is coming from a person with an acquired brain injury, and we had them come in to the lab after several months in the rehab facility. We started quite simple with just a few elements defined among distractors. We increasingly increased the difficulty as the person became more comfortable. And at the end of a few weeks, they were happily performing 360-degree searches, 180-degree searches for targets, and apparently enjoying their time playing the VR. This is our first neglect result, which is sort of our key target demographic of interest. And I guess the key result really is that you can see that using this raycast method, the headset is clearly positioned towards the right side of space. It's not something that we have seen in hundreds of tests of healthy people and demonstrations. So it's quite a striking pattern to see this for the first time. The other interesting thing here is that the eye position seems relatively evenly distributed. So that's a curious kind of question there. Is the person not seeing things on the left-hand side of space, but nonetheless moving their eyes to that position? If so, that would suggest that those object locations are known, but the information at those locations is inaccessible to people. With the controller position, we can see that the person is pointing to each of those different positions. So this person has no problem knowing that there is an object there, but potentially has a problem knowing what that object is. If we look at the accuracy data, we can see that the person is highly accurate for the first half of the experiment. And this is a 30-minute session, and this is the last 10 minutes, so 20 minutes to 30 minutes. So 20 to 25 minutes in the most difficult condition we asked them to do, they're highly accurate, all ones, maybe 1, 0. And then at a certain point, it became too difficult for that person, and they just kind of gave up, which kind of illustrates that you need to be very careful about precisely getting the difficulty right for that person, dependent on their abilities. But nonetheless, they're incorrect, but they're pointing to a location with an object. So it's not as though that location ceases to exist, but just that location doesn't have accessible information, or at least that's what this early pilot result suggests. Now, we have sketched out a basic session of what we think the VR may look like, and in the coming weeks, we're in the process of refining this setup. But the basic concept is to borrow something from video games in that we have a variety of conditions and that we have a progression of difficulty that keeps it interesting by switching things up, but also gives the person a sense of progression as they go through. Each of these grids represents locations at which objects may appear, and we can ask the question whether just 2 objects simultaneously appearing is enough to manifest neglect syndromes. We can vary the positions of those targets to ask the question whether the neglected space is relative or absolute. If it's relative, you would expect the same pattern of results for each of these, where if it's absolute, moving these targets and distractors further away may have differing results on the pattern. There are some things we can uniquely do with VR that we can't do with pen and paper. And one of those things is to present objects outside the immediate field of view and ask the question, how do people with neglect deal with objects that aren't immediately apparent on the retina? one prediction may be that if you can't see it immediately, that would mean that you're more relying on your own internal mechanisms. And if your own internal mechanisms have a bias towards the right side of space, then you might predict that this condition, where the objects aren't immediately apparent, shows the strongest neglect-like symptoms. We can look to see whether adding in more elements makes the task more difficult and shows neglect more apparently. Obviously, the left-right axis is where we expect most neglect symptoms to appear, but there are some reports that neglect may also appear on the vertical axis, and so we can directly contrast those two. One thing we can uniquely do with VR is to present objects in depth, near and far, and ask the question whether neglect plays out in near or far space. So here the blue objects are those presented nearby, and the red objects are those that are presented far away, but they're nicely and evenly distributed so that you're able to directly compare those two different depths. We can look to see whether neglected space depends on task demands by using an easy search mode where you just need to find a white one among greens, quite quick to do, or a difficult mode where you search for a white among all white. And we can also ask whether neglect is apparent during free viewing. So in each of these cases, and in the previous studies, they had people find a particular object. But what happens when you just say, look around and tell me what you can see, a task of minimal instructions? Do people show neglect under those conditions? So the idea is a relatively short testing period, which is suitable for a person with an injury that may be susceptible to fatigue, something like 30 minutes, and to start easy, become more difficult, and to mix things up and end with a kind of rewarding exposure to a happy environment. The next steps in this project include collecting data with patients with neglect and controls. And the controls are patients with brain injury without neglect, and also non-patients. And we're getting quite close to being started. We've cleared ethics at our two sites, Gold Coast University Hospital and Logan Hospital. We aim to compare pen and paper tests and VR data to see which best describe neglect. And we also aim to refine the attention atlas to better discriminate neglect and non-neglect attentional patterns. I'd like to acknowledge my collaborators at the Hopkins Center, Gold Coast Health, Metro South Health, Florida Institute, and the funding sources, NHMRC, Brunnings Queensland, and Metro South Health. Thank you very much for your time, and I'm happy to take questions should you have any.
Thanks, David. Great overview of some of the work that you're doing up there at the Beehive. Yes, so we've got about 10 or 15 minutes remaining. Happy to receive any questions either in the chat or feel free to jump online and ask them directly.
I'll start because no one else is going to. So, nice presentation, mate. Sorry I came in halfway through because we were indisposed to a discussion about setting up an AR training centre in rehab, which this thing fits perfectly in. And really the concept is that using advanced technologies, not look into the past, but look into the future, what rehab might be in 5 and 10 years' time. And I think this is a perfect example of what it might look like in 5 and 10 years' time. So congratulations on it. That's a statement. So in that regard, why the hell are you using pen and paper as the gold standard? Because it could be as useless. It's just because you've been using it in the past doesn't mean it actually is any good. It actually does what you think it's doing.
Well, that's a large part of the question. So to simplify the talk today, I really did focus on the pen and paper, which is the comparison that we're using. I neglected to mention that there was another widely used test, which is simply called a confrontation test. And that test is simply that you hold two fingers and you wiggle one finger to the left and the right in front of the person. And a person with neglect is able to see the finger wiggle on the right, sort of unilaterally right, unilaterally left. But when you do both at the same time, you have this phenomenon called extinction, where they're in competition, and so you miss the one on the left. So the methods used in the clinic are really born out of necessity and economy. And
no, they're not. Yes, they are, but they're also brought out because someone thought, oh, this seems like a good idea. I'm sorry, but that's no reason to do a test. You've actually got to have a good scientific foundation for doing a test, not this sounds like a good idea and I've got to get this test done quickly with the least amount of equipment. That's no reason to come up with a test. So the question I still ask you is, I'll ask it in a different way. What is a better, more neurophysiologically brain science test that could be done rather than something which is based upon what people do in a clinic? Because you can't trust what people do in a clinic for the reason that you just said, is that for expediency or someone thought this was a good idea.
Well, at the moment, we're testing to see how virtual reality compares with pen and paper. And obviously, we have the suspicion that virtual reality will outperform pen and paper.
So that was my question. What is a gold standard here? Because pen and paper I don't see as a gold standard, because you might have something which explores this in far more neurophysiological brain science, neuroscience perspective than what is done clinically. So, and I'm just wondering, if you come out to the very end and say, look, they're different, what's your conclusion? The conclusion is they're different. So the real question is what is something that really probes the brain deficits, the acquired brain deficits, in a really strongly argued scientific process to say this is better?
Well, that is the challenge, right? The scientific challenge. If you, we can leave the terminology aside, and we can just, rather than calling pen and paper gold standard, we can just call that standard, right? That's how we know at the moment in the clinical setting. Now, if we get different results of virtual reality and pen and paper, how do we know that virtual reality is necessarily better? Because we don't have the standard to compare it against. Like you're saying, that if the standard is flawed, then we don't have access to the ground truth necessarily. And so that's a lot of the challenge in this work.
So that's my question, I think. Right?
Well,
what is a better way of exploring the science of it than, and I do have an idea in the back of my head, but I'm happy for you to come up with suggestions.
There's virtual reality, there's neurophysiology, neuroimaging techniques. You could use EEGs, fMRI. There are neurostimulation methods. You could use transcranial magnetic stimulation, transcranial direct current stimulation. There are lots of tools in the arsenal of neuroscientists that could be employed in this space. And it may be that in future, it could be a combination of metrics, which actually provides the most informative information. It could be a combination of virtual reality scores and neuroimaging methods. But I think also along these lines, like what is the truth and what is the deficit? You can compare functioning between a regular person and a person with neglect. So that kind of becomes like a standard against which you can compare. But another approach could be to just ask the question, how well do people perform following their brain injury on everyday tasks, cooking, cleaning, going to the shop, driving, navigating public transport, and so on? Maybe it could be that we need to be looking more at the person's reintegration as a measure of the severity, and then the assessments can map onto the degree of the integration. So that question of functional relevance and correlations between the assessments and the person's integration could be important in reestablishing what the ground truth may be. And of course, it's always incremental, right? So maybe pen and paper was the ground truth, and then maybe virtual reality is the ground truth. But then there will be another technique in the future as we learn more that will progressively shift our understanding as we get clearer and clearer exactly what is happening with these people and their injuries. Thank you for the question.
I've got more, but I'll leave other people.
David, can I just ask you a question about your sort of strategy going forward in terms of growing your research program? You mentioned the names of the collaborators that you've got there. Can you just paint a picture of, what sort of disciplinary expertise you've got assembled there, and then what your long-term plans are in relation to funding and that sort of thing? Like, where are you sort of targeting your efforts in terms of attracting funding into your future research?
I've been so caught up in the details of programming code that I haven't thought so far about the larger perspective. In terms of the team, we have experts in the field of rehabilitation, in neuropsychology, engineers, cognitive psychologists, people with expertise in business, in particular clinical conditions, experts in stroke, leading clinicians in the field of rehabilitation. So it's fairly diverse. One thing I would say, like, I would enjoy more technical support. At the moment, we have a couple of people who are actually developing the technology, but it's quite involved. So I could imagine that a larger team would incorporate more people with an engineering background, for example. And we have plans in the next year to bring on board people from the computer sciences and computer art to help create a narrative, a narrative for the technology and a graphical sort of overlay to make it more like a game and more palatable as sort of a marketable product. We have been exploring, basic science funding and clinical grants. But something that I did for the first time, which is quite new, was to submit to the Startup Acceleration Program with Bionics Queensland. And I felt like I learned quite a lot in that process about another avenue outside of those traditional funding schemes, which Bionics Queensland would argue could potentially accelerate rollout. The idea would be to develop a marketable product and to sell that to enable a funding base for further development. In terms of sort of development angles, we've focused so far just on the assessment side of things, but it could be also that there are useful rehabilitation techniques that once we have a clearer picture of what the problems these people might face, then potentially we could circumvent the VR to try to work out a way in which we could use it for training attention and getting better after that. So that kind of commercialization element and that sort of application, interventionist style application, kind of lends itself maybe to more like a linkage stream potentially, that it would be industry partnership to bring that forward. Yeah, so I feel like, you know, it's still within the academic stream, so it will still be those traditional funding, government funding sources and clinical funding sources. But maybe especially if we get positive results, right? Maybe the commercial stream could help to supplement and create a more long-term security and stability for the enterprise.
If I can, I'm interested in who you think the industry partners might be, specifically, not in generic terms.
Well, I can name names if you
Perfect.
like.
That's what I want. That's what I want.
So like in the Brisbane context, for example, we know that there's a company called Real Serious Games. They're based out of Fortitude Valley, and their sort of mainstay is in industrial training. So like you have a complex work site, for example, you use virtual reality to explore and interact safely with that work site. Or also development projects. There's a new bicycle path along the Brisbane River down towards Hamilton. And in the planning stages, you look to see what this may look like in the virtual reality. And then you can assess whether that plan may be feasible, and you get people to come in and have a look at it and revise the plan if you find that there are any problems. So they've been working largely in that space, but you can imagine a company like that, if they thought that there was an opportunity to establish applications in the health area, that they would be quite interested in that. I do firmly believe that we do need to be in the business of making business and not trying to outsource it so much. So our chief competitor, well, I wouldn't really call them a competitor because they're kind of Goliath, right? There's a company coming out of Europe called MindMaze, and they work specifically in the virtual reality space, virtual reality rehab space. They have funding over $100 million that they've raised through hedge fund investments. And their whole take is that they're going to use virtual reality and the physical aspect of moving around in virtual space as a way to deal with neurological problems associated with motion, so stroke, paralysis following stroke, other types of movement problems, Huntington's disease, Parkinson's disease, and using VR as a way to rehab that. But, you know, Australia is quite small relative to a place like Europe or the States. And so the relative base is kind of smaller. It's a smaller market. But, you know, I do believe that we should be out on the forefront and establishing our own technologies rather than necessarily relying on people overseas to undertake that work on our behalf.
I absolutely agree with your last comment. Unfortunately, we are in a technological drought or void in Australia in rehabilitation, relied upon other people overseas for our technologies, and in the end, it is the commercialization of the technologies which make it into clinical practice, and it's the development of those technologies as they migrate into clinical practice, which changes practice. So I absolutely agree with you there. And unfortunately, putting your finger on actually rehab companies or engineering companies in Australia, it's a bit of a drought. The examples that we use are Restorative Therapies, which appears to be a US company and is actually now fully owned in US. Restorative Therapies does these FES and motorised assisted rehabilitation devices. Ironically, it's a cochlear spin-out company which grew up in Sydney. They couldn't do their stuff in Australia because of the backwardly visioned rehab industry or rehab profession here, and had to go to the USA to actually establish their technologies and sell it before they actually came back into Australia to sell. And unfortunately, that is a real sad story of technology development in rehabilitation.
Well,
And
yeah.
we can't let that happen again. There's another company which is a cochlear spin out called Saluda Medical. And they have a number of different technologies as well. And unfortunately, I don't know, I throw this out as a frustration because I see a hell of a lot of smarts, and what you presented today is wonderful smarts, really high-tech smarts and good science, but not being enabled in the rehab field, the actual application of rehab. And if we can identify some of these small companies in Australia and support them in the development of some of the technologies, which clearly we have the capabilities of doing it, and we actually lead the world in some of these cases, is if we can identify and create a training centre or something like that so these industries don't have to go overseas.
That reminds me of something that I neglected to mention. Maybe I was meant to cover a little bit about my background, but I will just briefly mention that I did a PhD in cognitive neuroscience at the Queensland Brain Institute, and cognitive neuroscience is just the field of working out brain behavior relationships, and I use neuroimaging and so on. The reason I bring that up now is because they had a lot of good guest speakers through QBI, and one of them was Peter Beattie, actually. And he made an impassioned speech about how the research standard in Australia is pretty high. We're hitting above our weight in terms of the funding available. We're good at generating new findings and getting our results published in high impact journals. But he said the gap is in that translation of taking those ideas and putting them into practice. And that's something that Australia is lagging the world at the moment.
Absolutely. And it's something that needs to be fixed. And I do get impassioned by this. That's a really nice word. And I usually full of expletives because I get so frustrated and angry at the situation in Australia. And you smart young things are going to be this future. And we need to work out a way forward here. And I think I see a smile on Rod's face because he's heard all this before. I know GCore, we try and adapt. We try to do these things, really make new technologies and put them into practice. And I think we need to be looking at some of these smaller companies and spin outs where we can just engender or lift just make them profitable and allow them to start generating some income and sell stuff back into Australia. Fortunately, our clinical trials industry is actually quite good because we don't have to get advanced regulatory approval to do class 2 or class 3 devices, medical devices. So you just have to do an ethics approval. So it's really good. So we do have an avenue for doing that, but we've got to get rid of our stuck in the mud view that we need evidence base to do practice. I'm sorry, but that doesn't take us forward. Sorry, evidence base is always looking backwards, and it's always using someone else's technology. What we need to be doing is looking what it's going to be in 10 years' time and develop the technology and develop the evidence for that.
Well, I think that was Bionics Queensland's point, that you can write all these research papers, but the academic process is slow. And by the time you've published that, then the field has moved on and left you behind.
Absolutely. And really what you're doing is playing in a technology field which moves so rapidly because the engineering and all the steam that goes into this just moves, really quickly. You've got VR, but VR is thing of the past now. So, there's extended reality and cross reality, and you're putting all these systems together in an integrated way to create the brand new rehab technologies. So you've got to be on that front edge all the time. So And I hear what you're saying about bringing a lot of these different engineering, and it might seem a surprise to many of the health professionals here, but there's lots and lots of different varieties and flavours of engineers, and they have each own different skills. They're the people and designers that allow these things to be translated into actual products in the real world. They're the multitude of people that need to be brought to this problem. And not just one engineer here and there and one scientist here and there and 20 health professionals and stuff like that. It's the balance has got to change. And I think that's what overseas does exceptionally well. So
one thing I neglected in my story, in this kind of simplification, was sort of the process at which we arrived about this application of VR for neglect assessment. We originally went into the clinical space and we said, we think that VR could potentially be useful, and we outlined a variety of different applications and some research supporting those applications. And it was actually clinicians that had suggested it. They said, look, we have this problem of neglect. There isn't a decent treatment at the moment. The things that we have just don't work. What can we do along those lines? And through the academic process, we actually pared it back a little bit, where we said maybe the lower hanging fruit, where we don't make too many outrageous promises too early, is just like a development in the assessment side, that if it's pen and paper, like maybe we can innovate there. And that seemed to be enough to persuade the funding bodies. But through that process of engaging in a dialogue with clinicians to work out what the problems were, we're now in a much better space. It feels less like we're coming in from the outside and more like we're part of a movement from within the clinical space. And that's kind of been difficult so far with academics, engineers on the outside and clinicians on the inside. And, you could imagine in future that there would be a department engineer in the rehab space that would be tasked with maintaining and developing these technologies. So that could be something of what the future might look like, of a more integrated approach of clinicians, engineers, for example, working together.
Yeah, I agree. The Engineers Australia, through their Biomedical Engineering College, I've identified possible 3 new strains of engineer who can work in this general health space, and one of them is a rehabilitation engineer. My real problem, I think that's a lovely step forward, but I think the problem is there are many flavours of engineer and many flavours of other technology professionals that need to be brought to bear onto this problem. Not just one trained rehab engineer or brain scientist or something like that. It's a team of people. We don't design cars using one engineer. It's stupid. It's not done. It's the wrong model that we actually have in developing health-based technologies. We need to bring that team of engineering STEM professionals to the table. So your example that the clinician said, we have a problem, that's what their role is. We have a problem. I wonder if we can do some new advanced technologies and things like that to solve this problem. Right? That's the dialogue that needs to be set up. But you also need clinicians who are forward thinking, not looking backwards. I try and find those is the trick. It sounds like you've got some in G-Core and ADAPT. We've identified them. They've come to us. They're the ones that you need to nurture, and you need to nurture those relationships. So.
Well, thanks, David. That's a very interesting conversation. Happy to continue it at any time. Just let me know when the opportunity strikes. I think we're a little bit out of time now.
Yeah, let's wind it up. But yeah, that ARC training hub sounds like something to follow up with between the two of you there. I think we're the only ones left in the conversation at this point. So thanks again, David. Appreciate it.
Thanks very much for the invitation.
Yeah, thanks, David. You're doing nice stuff, mate.
Yeah, nice work. Really enjoyed the talk.
See you later.
See ya. Bye.